Hello, and welcome to Meme Gen Monday here on Ants Are Everywhere. Today we're taking a look at gRPC-Haskell, which are gRPC bindings in the Haskell language. Previously, we've looked at the source code for gRPC, which is, I think, possibly called gRPC core. That's the C++, possibly also some C core source code for gRPC. And one of the things that Google does to implement additional frameworks in other languages that are not C++, is to wrap those, is to call the C++ code in the target language via some sort of foreign function interface. And one of the questions that I had, especially as I left Google, was, is there a way to use a framework like gRPC, or ideally gRPC, from a functional programming language? Because then it would be nice to be able to take a functional language and make microservices out of it, rather than having to use standard old REST style services. And so I looked around. gRPC-Haskell from this repo, Awake Security, seems to be the most recently developed bindings for Haskell. I also looked for some OCaml bindings. I think that was maybe a few months ago. I didn't really see anything. I saw some people asking if somebody could make some OCaml bindings, but I didn't really see anything that looked mature at the time. But I also don't know the OCaml ecosystem. So if there is something out there and people would like to see it, please let me know. Just some administrative points. First, today and tomorrow, I'm kind of working on a different schedule, trying to work around some conflicts. There's a chance I might get interrupted today. So if we're really on a roll and I get interrupted, I might have to stop the live stream and then resume the live stream later today. I guess we'll kind of play that by ear because we don't really have much of a choice today. And then tomorrow, actually, let me pull up my schedule here. And then tomorrow, in the morning, in the usual session, we're looking at React. There's a chance I might bump this back to 8:30 as well. I'll do that, I guess, before 5 p.m. Eastern today, if I do. And then there's some source code repositories in the news, which is that Twitter intentionally leaked. No, sorry, Twitter intentionally released their recommendation algorithm, and somebody asked me to take a look at it. So I thought it would be good to do that as soon as possible. This is the first time slot that I had available where I could really sit down and look at it kind of in an unbounded way without having to stop in an hour or half an hour or something. So we're going to do that tomorrow at 12:30. And hopefully there's some interesting stuff there. But I wanted to say that this is different if you've been following the Twitter news, which I haven't really, but I kind of looked up what was going on after I heard this was released. There's also a Twitter source code leak, possibly from a disgruntled employee, is what I'm seeing. But we're not going to look at that code. That's not open source code that has difficulties surrounding it. So some of the things that you might have seen in the news about the Twitter source code will be from the recommendation algorithm, but other things have been from the leak, and we're not going to necessarily see those probably. Well, we definitely won't look at the leak, and probably that stuff won't also be from the open source recommendation engine. And then after Tuesday, we're going to resume our normal schedule, which is on Network Wednesday. We're going to look at Wireshark. On Theme Thursday, we're going to look at Rules Haskell, which are the Bazel bindings for Haskell. And then on Fan Request Friday, we're going to look at some of the Firefox UI code, some of the stuff that puts pixels on the screen. And then next week on Meme Gen Monday, we're going to look at Gerrit, which is a Git-based code review platform that's I think a re-implementation of what's used internally at Google. And then on Tools Tuesday, we'll look at Git. On Network Wednesday next week, we'll look at IP tables. On Theme Thursday next week, we're starting a new theme. We're leaving the world of Haskell build tools and entering the world of language server protocols. And we're going to start that theme with a fan request, which is for the Rust LSP implementation, which I believe is part of Rust Analyzer. And then on Friday next week, we're going to look at Ardor, the open source DAW, digital audio workstation, multi-channel recording software. So that's the schedule. We're going to go ahead and jump into the gRPC-Haskell code. I guess before I begin, I mentioned we look at gRPC, and we also looked at the gRPC Python bindings, and that was the first repository we looked at, which is an official Google repository, to see how they chose to create a foreign function interface from in the Python world. So I'm expecting we might see some similar patterns here in the Haskell world, but I'm not sure. We'll see what goes on. It looks like this is recently developed. Some of the pull requests or commits are from a couple months ago, 3 months ago, and 2 weeks ago. Okay. And we can see in the languages it's mostly Haskell, but 8.4% C. I'll round that up to about 10%, like a tenth of the source code. There's also some Nix, which is presumably used for build environment stuff, and Python and some shell. And they say that this is a fork of another gRPC Haskell implementation. And I believe, so this is last commit was 9 years ago on this other Alesco card. I don't know, this other repo. And then I think Google has a gRPC Haskell implementation that seems abandoned 6 or 7 years ago. I don't know if this is related to the other implementations, but this is some other attempt to. It's an experimental library for using gRPC from Haskell. It's not ready for production use. So this is the Google version, not the Awake Security version. I believe the Awake Security version is intended for production use. And so the Haskell version from Google, I think this is from Google. It's certainly in the main gRPC repo. Also wraps the C library. The Google version does not generate RPC stubs, nor does it handle proto-serialization and deserialization. So and then the client-side features are just low-level API calls. So let's look if there's any interesting feature stuff in the README for Awake Security. Not really in the README, but maybe in this web page. I don't know. Okay. Well, let's take a look at what we see. We've got tests. Tests are good. We see in the main directory some default.nix. Not sure what that is, but I'm guessing some sort of Nix stuff. Nix packages, release.nix, shell.nix, some stack.yaml. And we looked at the stack build system, I think last week. Some, probably a setup script, setup.hs, a readme license, and git ignore. So we'll look at tests. We'll look at source network gRPC. I guess maybe some examples. Core and bin, and bench is presumably benchmarks. So for tests, I'm just kind of interested in how many there are, what's going on. We see several files. Some of them are, let's see what, a Python file, a test client.sh, which is, I guess this is a shell file, a bash file. Hi, James. How's it going? A test.patch, protalk, which is, protalk is a common abbreviation for the Google proto compiler. So the way that gRPC works in general is there's an interface description language, or an IDL, called protocol buffers, and you write your API in this description language, and then you use that description to generate code for the client and the server. So using the same proto files, you would generate Python source code and Golang source code and C++ source code, and in this case Haskell source code. And that way, in each of those languages, you you just kind of import that generated code, and you're off to the races. You don't need to implement things like deserializing requests and all that stuff. And then we have test server and test client and generated tests as the Haskell files. Actually, let's see which files are Haskell files. So generated tests, properties, test client, and test server. We'll take a quick look. Here's generated tests. Okay. I don't know what a test tree is. Maybe it's part of whatever, maybe Tasty. I don't know. Okay, so let's say server generation. So maybe this is testing the code to generate the server, and we have an input proto. So that's consistent with that. And proc, I think, is going to shell out, and it's going to call this essentially bash file, presumably, is the shell they're using, and check whether it's successful. So this seems to just be calling the proto compiler from Haskell and testing whether it's successful. Here's properties.hs. It's going to, I guess, just define main to be default main of, I guess, some test group of unit tests. So that seems like maybe just an entry point rather than having its own logic. Here's test client. And I see they have, let's see, proto3.suite. I'm not sure what that is. They got presumably a random number generator. That's cool. All right. That's normal call. I don't know what normal means in this context. But we've got a client. We're going to replicate M. We're just, I guess, replicate something 1,000 times using random RIO, maybe random input output from 1 to 1,000. And simple service request. This might be like a generated proto request from the API. Thanks. So James says, thanks for being a great code-based tour guide. Thanks, James. I try. I'm glad you're enjoying it. And then we're going to, I guess, get some res response, and then it's a case of either an error or a normal response. I guess if it's a normal response, we'll check the status. And if it's status okay, and we saw status in the gRPC code, it's basically the status okay is basically the same as HTTP 200. And then we'll do whatever we're supposed to do if we have a normal response or an okay response. And then I guess we're going to test streaming call and some other stuff similar. So this is probably just going through the different functions from the API. Thread delay, what is this number? That's thousands, 100,000, millions, 10 million. 10 million is what? I don't know. Maybe nanoseconds? What is nano? Let's see if 10 million nanoseconds is reasonable. Oh, it's much less. Okay. In seconds? 0.01 seconds. All right. All right. That'd be 10 milliseconds. That might be the right sort of delay. And then with gRPC, and then we've got this, I guess, Lambda with client gRPC client config. I guess we'll pass in some config that tells us we're listening or maybe calling on localhost. I guess if we're the client, this probably means that the server is listening on localhost, and this is the port. It's a common gRPC port. Nothing. I don't know what those arguments are, but I guess they're essentially null. And then we're gonna do the calls, it looks like. Okay, so that's test client. And Andy says, thank you for my vids. Thanks, Andy. I'm glad people are appreciating it. I honestly didn't I didn't know what I was doing. I honestly didn't expect people to be as into them as they are. So I really appreciate it when people let me know. So here's test server. What do we got? Okay, so this is maybe the server itself. Okay, we've got handle normal call. Again, I don't know what normal is. Server request, normal server, simple service request, simple service response. So these are the types, right? So it's going to take a whatever normal is, and a request, and a simple service request and a simple service response. Maybe simple service is the name of the proto service. And it's going to return an IO of server response, normal, simple service response. And the implementation is going to be handle normal call of server normal request, meta, maybe like metadata, simple. And then these last three arguments, I guess, are become a tuple, simple service request, request nums. And then we have pure here, which we saw before, I think in applicative, which kind of like takes a non-applicative thing and moves it into applicative. I think here we're just in the IO monad, so maybe that also happens in IO. Maybe it's in general a way to get stuff into the monad. I'm not sure. Maybe there's an applicative here that I'm not seeing. At any rate, we're going to pure something, and we have server normal response, server service request result, empty, which might be a mvar, maybe an empty mvar. And we saw before that mvars were like these mutable variables in Haskell, and a status okay, and status details are the empty string, where result equals sum of nums. So ultimately, the result is we're going to sum some numbers. And I think, let's see if we can find the proto file for these tests. Here, okay, simple.proto. Yeah, okay, simple service. Okay, great. All right, normal call is the name of the RPC. All right. And it takes a request. The simple service request just takes a string and a num. All right. And what is the string? Do we do anything with the string? Request nums. Is the request called? Yeah, the string is called request. Okay. So whatever the request is, do we do anything with it? I'm not sure, but we call sum of it. So we're going to add the nums together, I guess. All right. And then is there anything mysterious here? So server normal response. So we're the server. We're going to handle the call. So I guess we're going to create a response that has this form, maybe. Simple service response, request, and result. So the response is also a string that's called response. And I guess we're just passing it in as, I guess we're just passing whatever request was back into the response, maybe. And result is just going to be equal to the sum of whatever nums they gave us. What is nums? Nums is a repeated number. So they're passing in an array of numbers. We're passing back a single number, and that's the sum operation. Okay. And then we've got some error handling, like left IO error and some other stuff. Exit var. I don't know what exit var is. Okay, so exit var is going to be new empty mvar. So we're going to get a new empty mvar. And then where do we use that? We're going to take the mvar exit var at the end. The simple service done. I guess when the client says they're done, I guess exit var is going to tell us whether to exit. We're calling fork IO, which is presumably some way of forking different threads. And then I think the rest is probably pretty straightforward. Maybe let's look at a streaming request. Handle server streaming call. Let's handle bidirectional streaming. So we get server. So everything starts with server request, and then a primed thing that seems to indicate the name of the, what is this? The name of the request? I'm not sure. Here, the RPC the name of the RPC function is lowercase, but here it's uppercase. So I'm not sure exactly what's going on or why it's primed. But then we also have a simple service request, a simple service response. So these are just the things that are I guess being passed in. And then we're going to do some IO. And the IO is somehow parameterized by the type of call we're getting. And so we have this server BiDi request of the call, the received request, I suppose, and the send response. And it's going to equal go, where go is, I don't know how this is different from kind of like do notation, but we're going to have this go thing and this where clause, and go is going to be equal to receive request, this thing, which I think is like a monadic, let's look at monad bind in Haskell. I think that's a monad bind type operator. No, am I misreading this? Who do we have? We have two greater than signs and an equal sign. So I typed the reverse. Okay. Yeah. A class monad, and then in monad, to implement a monad, you need this this operator, which takes an M, so an A in the monad context, and a function mapping A to the monadified B, and it returns a monadified B. So whatever it's doing, it's presumably taking A, monadifying it, I guess, and applying whatever this function is. Is that what it's doing? No, but it takes a monadified A. So I guess it's maybe unmonadifying it and then applying this function. I guess that's what it has to do. What is it called? Okay. The two varieties of bind, okay, are greater than equal, and just greater than without the equal sign. So what does the without the equal sign do? Without the equal sign just takes a monadified A and a monadified B and returns a monadified B. But what does it do with the A? I'm not sure, and I don't think monadified is a real word. That's just my glossing of what's going on. So okay, so that makes sense. There's some version of bind. I'm not going to worry about what happens to this M of A right now, just because I'm short on time. So I'm sure it isn't. I'm sure the two different kinds of bind are interesting, and I think we'll come back to all that sort of Haskell stuff as we go along. All right, so so we were handling bidirectional streaming, and so we're gonna, I guess we've got this receive request, and we're gonna enter monad land where like the IO, I think monad is what we're doing, unless the whole monad is like IO of a bunch of stuff. I'm not sure how to think about it conceptually, but we take a request, and we're creating this lambda, and we're calling case request of. If the request is an error, is that, yeah. I'm not sure how we would be called with an IO error. We're going to say status is canceled, I guess. And with the status details of IO error. And then we're going to try to send this back, I think, as a proto message to the client. Since we're populating status details and not just printing it, logging it on the server side, it seems like. If the request is nothing, then I guess we just return status OK and the empty string. And if the request is just a simple service request, so just, there should be like a maybe here. So maybe, perhaps the maybe is implicit somehow, but if we get a simple service request with a name and some nums, then we're going to do send response, and we're going to construct this service response, and then we're going to call go. And I said I didn't know how this was different from do notation, but since we're calling go recursively on the success case, I'm going to guess that this is just an infinite loop where we are recursively calling back to go. So I've seen this before in functional programming, where go is, I think, called loop. It's a way of doing an infinite loop. I think that's what's going on. So that's test cases. Let's see if we can look at some implementation details. I guess we'll skip examples because we saw some examples in the test cases. Let's look at bin. Bin just has this shell file. So we'll ignore bin. And so the two things we're looking at are source/network/gRPC, and we have high-level.hs and presumably some more details about the high-level module in the folder. And then we have core. And I think I have about half an hour before people come to my house, some contractors. So what's the best way to use this? So let's look at core and see what we can ignore. We're going to ignore the Nix stuff. We're going to ignore the Cabal stuff, the setup, the README, and the license, and the tests. So let's look at cbits and source network.gRPC. Let's just peek at what's inside the include file. And the include file is gRPC-Haskell.h, which is, the name sounds like it might be important. So here's cbits. And what do we got? So here's cbits. All right, so we're going to include some header files. So this is C, and we have a C file extension. And what are we including? We're including gRPC.h. I can't remember off the top of my head what was in that particular header file, but that seems like a main entry point. And by main, I mean primary, not like the main function. We're getting the gRPC byte buffer, which is presumably some sort of byte buffer that's optimized for the gRPC world. We have gRPC security, which is going to do security stuff. gRPC impl code gen gRPC types, so types, compression types. Slice we looked at, and slice was it's essentially an array or a buffer, but I forget exactly what made it special. I think possibly it was usable from, like, viewable from different threads. Basically, if I recall correctly, it's optimized for doing things like calls, where you might have some data that's reused, or you don't want to allocate too much, that sort of thing. And then some standard IO, standard libs, string. And then we're including gRPC-Haskell.h, which is, I think we opened. Did we open that? Yeah. Okay. So let's look at this. This is we are not in gRPC-Haskell.h, even though I just mentioned it. We are in gRPC-Haskell.c. Let's do .h first, actually, since these seem to be related in the sense that the C is the implementation of the H file, even though they're in different directories. Okay, so what do we have in H? Just a subset of what we imported in the C file. Okay, and just looking at types, we have a bunch of gRPC events, or rather two gRPC events, a gRPC call, a slice, and some slice-related stuff, it looks like. We can presumably free the slice. We have the byte buffer, time spec, which is maybe like a timestamp. Slice, status code, metadata, call, slice, arg, auth, property, channel credentials, and credentials, and gRPC metadata. Okay. Now, if I remember correctly, the Python code had like direct access to the gRPC queue. I forget exactly what they called it. I think maybe the completion queue. gRPC had this special queue, which was like a lock-free way to essentially send stuff on the wire, and you could continue to add work to the queue while it was working. And I believe that the Python implementation had like direct access to that queue, but it doesn't. Oh, no, we do. Okay. scratch that. Okay. So I should have looked at these functions first. All right. So we have gRPC completion queue next, and we're going to take a gRPC completion queue, star CQ. I guess I don't see where we created the queue, but I guess QNext creates an event. And I was only just now looking at the return types. So I missed the completion queue. Okay, so we've got the deadline as a time spec. So GPR is like the Google runtime. It has a bunch of utilities that you would use in C++ code, or rather C code throughout Google. And I think when we looked at it in the gRPC video, we saw that there was a GPR and like a GPPR or GPRR or something that had a duplicated letter for the C++ version. So I think since no letters are duplicated here, that this is just the C version. So maybe we are in straight C. And we have void star reserved. I don't know what reserved is. Maybe it's like reserved memory. Or maybe sometimes you see the word reserved for like this argument is reserved for something that I might not be using. All right, and so we also, so we can call next on the queue. We can pluck the queue, which takes a completion queue, a tag, and tags are things we saw in certainly in the gRPC Python video. We might have also seen them in the gRPC video. They're kind of like I think they're a little bit like a type for the event that's like passed in as an argument rather than being like part of the type system. That's vaguely what I recall. A time spec for the deadline and reserved again. And we can create a call. A call being like the C struct or object that we are going to, that encapsulates the call, like the function call we're going to make over RPC. And to create a call, you need a channel. You need to specify which channel, I guess, you're going to create the call on. A parent call. I forget exactly what a parent call does, but something, I guess you get some sort of tree or graph of calls. Maybe the ability to reuse or inherit from the parent as an optimization. A propagation mask, which includes propagation information, like how to propagate the call, if I remember correctly. The completion queue, presumably that the call is going to be attached to. The method to call, which is a const char star, so essentially a string, a const string. The host, which again is essentially a constant string that the create call function is not going to manipulate, and a deadline, and reserved again. Then we can allocate a slice, I guess, of a given length. We can get the length of a slice. gRPC slice start. Returning UNA. Maybe this is just getting the start or the beginning of a slice. We can get slice from a copied string. The naming sounds to me like you're going to pass in a copied string, but presumably what it means is since you're passing in a const char star, that it's going to copy the slice from the string. And similarly for buffer, and you're going to pass in the length for buffer because it's not null terminated, I guess, like a string is. You can free a slice from Haskell, create receiving byte buffer, which is a star star. I guess gRPC buffer star star. We can destroy the receiving byte buffer. gRPC byte buffer reader read all. I guess we can consume everything in the byte buffer, and we get a slice. I guess like a view into the byte buffer. We can destroy a time spec. All right. GPR inf future. I vaguely recall inf future might be infinite future, which is maybe a way of saying that there is no deadline. GPR now. We're going to pass it in a GPR clock type. And presumably this is going to be now, time.now or whatever in other languages. We can convert time to milliseconds by, we've got a time spec, which is this Google thing, and we can convert it to milliseconds. Presumably milliseconds since like 1970 or whenever what is the Unix time? January 1970. This is not an ISO date, right? If we're gonna have the 1 from the January, maybe we should maybe somebody should convert this to an ISO date. I think ISO data is the year first, right? Unless I'm going crazy. The most to least significant order. Year, MMM. Those superseded is the standard that originally introduced the all numeric date notation. Okay. So I think that's still the thing that people used. That people use. Well, I don't know. I'm not going to spend too much time on it. It's just kind of riffing on, just kind of trying to inject some lightness here. All right, and then we can get seconds to deadline, milliseconds to deadline, infinite deadline. I don't know how that's different from infinite future. Or I'm not even positive. I'm not 100% positive this is infinite future, but I'm pretty sure. We can do some clock conversion. If we have a time spec and a clock type, I guess we can get another time spec that is somehow different. Maybe time spec has a notion of which type of clock it is. We can create a metadata array, and we get a pointer to a pointer if we do that, which makes sense since the array itself is a pointer, I guess a pointer to the first element, and this will be a pointer to the this will be a pointer to the array. Some more array stuff. We can alloc metadata. We can free metadata. I'm just trying to get a sense of what do we need to do from Haskell? What do we need to understand of the gRPC C code in the Haskell world if we want to implement something like this? This is essentially the question I'm trying to get at. People sometimes ask me why do I read code this way versus some other way? I can probably do a much better job of explaining the whys, and I try to do that a little bit. If people want me to explain more about the reasoning behind the strategy, I can try to do that as well. But the strategy right now is I want to just get a sense of assuming that the average Haskell developer is not also a C or C++ developer, then this file is kind of providing a view into the C of the stuff you would need to know if you were writing a gRPC service and something went horribly wrong or whatever, and you were whatever the equivalent of SRE is in your organization, and you needed to debug stuff. This is kind of like the you can view this as a list of the C stuff that Haskellers need to know about in case they're called upon to kind of debug the interface between Haskell and C or whatever. So we've got metadata, OP send message. I'm not sure what op is here. Maybe just operation, gRPC op array or options, and a size and a payload. We can close the client. Some more initial metadata. We can receive a message. Okay. So this is probably the actual receive and send stuff, I would guess. But there's no completion queue. So we had the completion queue up here. That's for doing things like creating a call and getting the, let's look this up. Op receive message. Receive a message. 0 or more operations can occur for each call. So I'm actually in the PHP documentation. So that's just what came up first. So op, I guess, is operation. Completes after all bytes of the received message have been read. So I guess that this interface is, we're going to give it a buffer to load the message into, and it's a void. So this is, I guess, an out parameter, or one of these is an out parameter. And we are passing it the size, I guess, that we can fill up from the message. Receive status client. And we're going to get, I guess, a gRPC status and the details back. We can close the server. And we can send the status from the server. Cool. What else can we do? Create status code pointer. Deref a status code pointer. Destroy status code pointer. Create call details. I don't quite remember what is in call details, and we can destroy the call details. And we can watch the connectivity state, which we need a channel and a connectivity state, which is passed in as a parameter and is not a pointer, I think. So it's not an out parameter. So I guess we're saying we're going to watch this, maybe watch for this particular state. The last observed state, a deadline, and a completion queue, and a pointer to a completion queue and a pointer to a tag. Okay. So somehow this is going to watch the connectivity state. I guess we'll get some sort of message, maybe from the completion queue. I don't know. It's void. So one of these has to be an out parameter if it's going to return something essentially, unless this is just registering our desire to watch it. I don't know. Okay. We can get metadata, create a registered call. So registration in gRPC, I'm not sure really what it does, but when you have a server, you can register that this implementation of the API is the thing that handles the server request. And then I think you can also have unregistered implementations. I don't know when they're used, but that might be more for things like if you have a utility that's going to there's like a public version. I forget what it's called, but sometimes you get these utilities that let you make any RPC request or any REST request kind of for debugging. And so for those, you may not want to register everything, possibly. Let's look up gRPC registration. There's something about reflection, maybe? Register reflection service? I don't know. I'm not sure. Again, just because of time, I'm not going to dig into this. Okay. So anyway, a registered call, I think, is like if you follow a tutorial, I think it always tells you to register things. So whatever unregistered calls are, I think that's not the ordinary state of the world. Anyway, to create a registered call, we've got a channel, a parent call, kind of the same stuff we had before: propagation mask, registered call handle, and a completion queue, and a deadline, and reserved. Okay, call details get method. I guess this gets the method from the details of the call. You can get host, get deadline. We can register a method, which is going to take a server and the method and the host. And that, I guess, will tell the server that it's handling that method on this host. And then a method, gRPC server register method payload handling. Whatever that is, some payload handling stuff. And then enum supported ARCHI. And C2HS is, I think we've run into it before, but it stands for, I think, C to Haskell. It's a way of taking a simplified file. Let's look it up again. At any rate, it helps you generate like the FFI stuff. I forget what kind of file you input. It extracts interface information from C headers and generates Haskell code. Okay, with foreign imports and marshalling. So I think this is similar to what we saw in Cython, where we had some Cython file that was going to somehow generate the more fiddly FFI stuff. So C2HS doesn't support const pragmas, referring to hash-defined strings. So we use this in enum as a workaround. These are converted to actual gRPC hash defines in translated argkey in gRPC-Haskell.c. Okay, so there's some workaround for defines, or I guess for const pragmas. And these are things like compression algorithm key, compression level, user agent, prefix, suffix, and max receive message length and max metadata size. Okay, so we can create an arg array, create string arg, create int arg, destroy arg array, gRPC auth context property iterator, SSL server credentials. So we can create some SSL stuff, credentials. Let's see, get metadata. Okay, So there's actually not a ton here. But what's interesting is we do have direct access to the queue, and we'll have to malloc and dealloc some stuff or free some stuff. And we'll have to work directly with some of the lower level types like the time spec. And then there's some fiddliness around some of these constants from the C source code. Okay, here's the C implementation. And this should be pretty straightforward now that we've looked at what the header file is up to. So for example, gRPC-Haskell free is going to take a debug message and a pointer. And if debugging is turned on, we're going to print out stuff about what we're freeing. And then we're just going to free the pointer. Completion queue next. We're going to malloc the gRPC event. And then we're going to, what is it called? To return. So, and then we're going to assign it to be calling gRPC completion queue next on, this is the same function. There's no underscore here. So I guess this is the C function that the Google people wrote. And the underscore version, I guess, is the Haskell linking function somehow. And then we're going to just call that and return it. And I think, I'm going to guess things more or less, everything has more or less the same flavor. Where we malloc something, we call the equivalent Google operation, and then we return the thing we malloced. And we're seeing this here. Slice unwraps just unwraps a slice, I guess. Doesn't need to allocate anything. And that seems to be everything that's going on. Or maybe here. Let's see. Receive initial metadata. It's going to do something different, right? So we're going to increment op somehow. Or what is I? I guess we're going to go to the next operation. So this is like pointer arithmetic, I assume. We're going to set op to gRPC op receive initial metadata. I guess we know what the operation is because that's the function we call. And we're going to set this to array. I think I was confusing two concepts in the gRPC code base. One is the completion queue, and the other is this call combiner that we had seen in the first gRPC video. And so as I was learning more about like what the completion queue was up to, I found this great talk, and I'll link it in the show notes and also in the show notes of the original gRPC video. Let's see if we can find it here. This one also might be good. This is 1 year ago, but this is the one that I had seen by Sri Kukabotla, maybe in Jayant Kohli. And this talk goes over, among other things, things like the completion queue, with the batch operations and stuff like that. So that's probably worth checking out. And I'll also check out this other deep dive that is more recent. And if it's also useful, I'll post that. Okay, so that's that stuff. Hello, inevitable pipe. How's it going? All right, so we're back. We are, I think, in gRPC_Haskell.c in the /core/cbits folder. And we had all these op operations, and these ops are also covered in the gRPC deep dive talk. And what I understand from the talk is that operations are batched together, and they go on a completion queue as a batch, and then you essentially pull, or the gRPC C code pulls the completion queue for being to get notified when that batch is done. And so these up like send let's see, somewhere there should be send initial metadata. Okay, so send initial metadata, send message, close client, and receive initial metadata. These are some of the core operations. Actually, why don't I pull up that talk again? Let's see if we can find the slide that shows these operations. Or let's see. Do you have the slides? Or maybe I can just look up gRPC. Let's just try doing it like an image search or something. Maybe the transport explainer has it. No. So let's see if we can find this in here. I'll mute the volume. Okay, so client and server perform ops in batches. They can start all operations in one batch or split them into multiple batches. And it depends on whether you're sending like a unary or streaming RPC. That's one thing. And here are these are the only operations, i.e. ops, that could be performed on a call. So under the hood, at the like lowest level, I guess, the things that gRPC actually understands are send initial metadata, receive initial metadata, send message, receive message, send trailing metadata, and receive trailing metadata. So I guess we can think of the metadata as like, we're about to send you like actual messages being the things that are like function calls. So these are like setup, receive server information about setup, then actually send the message, receive the reply, and then send some like teardown information. And then whether you send one message or more message, that's the thing that differentiates, if I understand correctly, between a streaming RPC versus a unary RPC. So unary, we send one message, we get one back. Server streaming, I think we send one message from the client and then we get multiple messages back from the server, vice versa for client streaming. And then bidirectional streaming, we just keep the pipe open and send messages back and forth. So that's what's up with these ops. I think that was I think I had asked that, or maybe verbalized that question before I left. And so we see that here in the C bits, the interface between Haskell and C in gRPC-Haskell. So these are, so that's what's going on with these. More op stuff. And then I think we had decided that most of this stuff was straightforward modulo understanding the header file. Once we understand kind of the stuff that's exported, a lot of the C code is just doing things like ultimately calling the, a lot of the foreign function interface between Haskell and C is doing straightforward stuff like calling the corresponding C function. And as we're scrolling through this, that seems to be what I see. So if there's nothing, there doesn't look to be anything surprising here. So like once we know what the function is called, we can kind of imagine what its implementation is going to be. We don't really need to look deeply at the implementation, I think. So let's close out the C stuff. That might be the only C FFI stuff here. I'm not positive, but we'll see what else is here. And so now we are in Haskell land, it looks like. So we have low-level.hs and unsafe.chs. CHS is maybe C to Haskell, C to HS. So this might be something that's going to import C, or maybe CHS. Let's see, look up CHS Haskell FFI. Yeah, seems to be part of the. No, I do not want to include results for that. Okay, we'll look at it. But this is maybe like the Haskell side of the border between C and Haskell, or like the beginning of the Haskell side, and then calling them low level and unsafe. Maybe it means unsafe from like the Haskell perspective, like you're kind of like maybe in Rust, unsafe means like we're escaping the guarantees of the higher level language and going into the lower level language. So this seems to be boundary things. And then in this folder, we have source/network/gRPC, and we have high level in high-level.hs. And since we've seen the low level, maybe the thing to do is to look at the high level next, and they're going to presumably kind of meet in the middle. And so we'll do low and then high, and then we'll look at how they meet in the middle. And then David Connor's asking, don't RPCs necessarily create side effects and remote ones? Well, yeah. So they send messages, they send bits on the wire or in the airwaves if you're using radio or Wi-Fi. Yeah, so they necessarily create side effects. In Haskell, the way that you typically at least deal with side effects is you stuff them all into a monad. I think usually the IO monad. And so one of the things we should see is that everything that's ultimately sending stuff on the wire is going to be have return type IO of something or other. But the benefit in again, I'm not a Haskell developer, but my understanding, the argument for the benefit of that approach is, yeah, sure, you're going to have side effects, but the API, the language and the types itself make it clear where those side effects are. Whereas in the C function, you can just pop side effects here and there, and it's not visible like to the type system or to static analysis. And so one of the things you see, I think, show up in Haskell is like you're taking all of the side effects and kind of like pushing them to the boundary of the program, and then internally in the program, as much as you can, you use more pure functions. So I think that's kind of the pattern. So we'll now that I've said that, maybe we can try to see if that's what we see as well. All right, let's see. Okay, so here we are in high level. Let's open up highlevel.hs, and I guess we'll also open up the folder, just because this might get complicated, I guess. So we have client in the high level folder. We have server.hs, generated client.hs, in the server folder. So what's in the server folder? It's just unregistered.hs. So how do we want to do this? Let's look at generated first, then client, then server, and then we'll look at unregistered, and I guess that'll be good. Okay. So here we are in highlevel.hs, and what do we have? We've got metadata map, method name, status detail, status code, gRPC IO error, gRPC impl. These are, I guess, things that are exported by the module, if I understand the syntax correctly. And at the bottom, we just get imports. So this highlevel.hs is just kind of like setting up the module, right? Okay. All right. So this is like setting up the module. So metadata map. All right, so what do we have here in high level? We've got a metadata map, which is, I guess, going to be some sort of, what's the word? Like a hash map? Like a place you can, like a key value store for metadata, I'm going to guess. We have method name as a type, which is presumably just kind of like a string. Status detail, status code. So these are, I guess, Haskell-y versions of some of the stuff we saw in the C code. So errors, make handler, or MK handler. I'm going to guess it's make handler. Somehow we're going to, we'll see what that does. Service options. And then on the server side, we have handler options, server call cancel is expired. The client has normal request result. Again, I don't know what normal is. Client call cancel. And I don't know why some exported things are uppercase and why some are lowercase. Maybe some things are like functions and some things are like data types. Maybe look that up. Haskell capitalization conventions. Types start with capitals and functions start with lowercase. Okay, that's one convention. I don't know if that's what they're using here. Names, especially global ones, should be descriptive. If you need long names, write them in lower camel case. For type class, constructor names are usually written in upper camel case. In standard libraries, some parts of the code use snake case. Okay. And then, right, so authorization stuff and authentication stuff, server authentication or authorization, client auth, and some streaming stuff. And then we import some things. This is going to import high-level.server, high-level.generated, and low-level. Okay, what is this first tab? I think we can close this out. All right. So I think I have everything in here, right? Let's close this tab here, which is, I think, just a folder. So here we are in generated.hs. Now, I don't know if this is a generated file. Let's scroll through. This doesn't look too generated, but we're going to export some stuff. Some of this looks like the same stuff we exported elsewhere. I don't know if that means it's re-exported. I guess that might mean that. But we do have some language pragmas things. I forget exactly what these are called. I think I figured it out last Haskell code base I looked at, and then I promptly forgot what they're called. We have type families, which I've seen before as some sort of family of types. Data kinds, rank n types, and overloaded strings. So rank n types and type families, I think, are like fancier types for Haskell, where, but I don't remember exactly what they do. But if we're in a source file called generated, and we have these fancier types, then this might be where some of the complexity is in the code base. But it's not long. The file doesn't have a lot of lines. So there can't be too much insanity going on. And then we import several things, including low level and low level call, and whatever numeric.natural is. Maybe natural numbers? I don't know. Okay. So we have data gRPC impl. So used at the kind level as a parameter to service definitions generated by the gRPC compiler with the effect of having the field types reduced to the appropriate types for the method types. So kind should probably be like a type of types, right? So I think kind is typically used to escape kind of like self-reference paradox. Let's look up Haskell kinds. A kind. Wikipedia says, in type theory, a kind is the type of a type constructor, or less commonly, the type of a higher order type operator. A kind system is essentially a simply typed lambda calculus one level up, endowed with a primitive type denoted star and called type, which is the kind of any monomorphic data type. Ordinary types are also called monotypes or nullary type constructors have kind star. Higher order type constructors have kinds of the form, I guess P implies Q or P to Q, where P and Q are kinds. For example, int. Okay, so this is consistent with what I said. We're going one level up in abstraction. So to avoid things like, to avoid things like the Barber's paradox or like talking about the set of sets and all of that self-reference stuff that shows up in logic, I guess. And so int is a type in Haskell, and it's, I guess, kind, assuming that colon here means kind, is star, and maybe is of type star to star. So maybe, okay, so maybe takes another type, like maybe of bool, is of type star. So somehow we had maybe, and maybe is going to take a type as an argument, in this case bool. It's going to return another type, is what I think. Sorry, yeah. I think I'm saying type and kind correctly, but I might mix them up. So the kind of maybe is star to star, which means it's going to take a type as an argument and return another type, I think. And then maybe of bool is we've applied that argument. And so now we just have a star kind. And a function from A to itself has a just star as its kind. The empty list is something that it behaves like maybe somehow. It's going to take a kind and return another kind. And arrow, I guess the function arrow, is going to take two kinds, one on its left side and one on its right side, and return another kind. So that's the sort of thing that kinds are up to. And I don't know what that means in this level, in this particular context, but we can read this again. It says, used at the kind level as a parameter to service definitions generated by the gRPC compiler. So the gRPC compiler is going to generate service definitions. Presumably, it means like the proto compiler. So we have some like simple service, I think was the example, or like in the gRPC code, we saw some sort of math service that added numbers together. And so somehow, whatever gRPC impl is, it's as a parameter. So service definitions, I guess, are kind of like some of the kinds we just saw where they take a type as an argument and might produce another type, or they might take a few types as arguments. And somehow this is related to that. And presumably either higher order types or type families or data kinds is going to allow us to talk about things at this higher level. But that's all hand wavy. I don't really understand the details. Okay, so make handler. Oh, okay. So make handler is a type family. Okay. And it's got this implementation, which is of type gRPC impl, which means it's either a server impl or a client impl, I guess. And a method type, which is of type gRPC method type. And an I and an O. Okay. So GHC does not let us partially apply a type family. So I guess there's no like currying in type families, maybe. However, we can define a type to use as an interpreter and then use this interpreter type family fully applied to get the same effect. Okay. I don't know what I and O, maybe input and output. Maybe like send and receive or vice versa. All right. And so, however, we can define a type family to use as an interpreter. Okay. And so we have different make handlers. We have client streaming, server streaming, and bidirectional streaming, which means normal must mean like unary, because that's the other type of message in gRPC. So I guess normal means unary. So we have server. So make handler of server implementation of unary. I guess IO is going to be server handler of IO, and server implementation of client streaming IO will turn into server reader handler. Then there's server writer handler and server read write handler, and they all take IOs. Okay. Again, I don't really follow, but I can kind of see the sort of thing that they're trying to do in a very hand wavy and unclear fashion. Then what do we have here? Service options. Some data type, essentially a struct of things that you use to configure a service, things like host, port, whether to use compression, initial metadata. Metadata to send at the beginning of each call. Okay, so it's a metadata map. I didn't realize that you would, if you're sending this if you're sending the same metadata on each call, I don't know if that's the default or if calls might change metadata like as the program is running. I don't know what gRPC expects, but it seems like you could at least, pass in a metadata to serve at the beginning of each call, and we get this metadata map, which I think I had hypothesized is kind of like a hash map, like a key value store of some sort. And an SSL config and a logger and like a bound on message length and a metadata size. And then we've got some default options. And the 5051 is the default port. Default host is localhost. Compression is default false. User agent prefix. I guess the user agent we're going to send is we're going to say that we're gRPC-Haskell. And we're going to divide by 0.0.0. I guess that's to, if you don't change this, then maybe that's a way of saying that I don't know. Are we actually in zero? There must have been a release, right? That's different from the zero release. Let's double check this before speculating. No releases. Okay. So what about maybe branches or tags? Okay. So maybe we are on 0.0. All right. And metadata is initially empty, et cetera. And then with gRPC client, it's going to take a client config and a client. The client will return IOA, and together all of this stuff returns IOA. Okay, so this is somehow a way of taking the client and its config and I guess bundling them together or something. All right, so I don't understand this higher order stuff, but I think that mainly it's there to kind of make we don't know everything about the gRPC service we're implementing. So I guess in that sense, the types are going to come from the compilation of the protobufs. And my guess is that all of this stuff is kind of a way of being able to talk about the types of servers and clients, even though we don't know. There's essentially like a blank space that's going to get filled in once we compile the protos. And I think that this is kind of like a way of allowing us to talk about that blank space, like at the type level in a way that the type system and the compiler understand. And then being able to plug it in later or something along those lines. So actually, what was that file again? Generated. So this is maybe for dealing with generated code. Here's the client.haskell. Okay. And it actually looks pretty nice and clean. Let me just scroll down to get an impression of the file. All right. So simplify server streaming. Okay, we'll look at that in a bit. So we have client request. And some data types like client request. We have service client, registered method, and some imports. And we're exporting a bunch of stuff. LL is maybe low level. Maybe we're re-exporting the low level client that we imported. We're importing low level. And blah, blah, blah. Import gRPC low level as LL. So I guess it may not be entirely low level if when we import high level, we can get access to the low level thing. So we can, like, I guess, peek at the implementation in some sense. We have control monad. I'm not sure really what control monad is, presumably like fancy-ish monad manipulation stuff. We get things like managed, lift.io, and managed. All right. Lazy byte strings and some low-level stuff. And then Proto 3, I don't know where that comes from, but this is presumably protocol buffer support. Proto 3. Let me look up Proto 3. Okay, so Proto 3 brings up protocol buffers. Is it a Haskell thing? Okay, so this is another repo that does provides a higher level API to the Proto 3 wire library that supports type classes for encoding and decoding messages and instances for all wire formats identified in the specification. A higher level approach to encoding and decoding based on GHC generics and a way of creating .proto files from Haskell files, from Haskell types. So I guess you can somehow write a Haskell file and then use that to create .proto files. Okay. I think there's also like a, I think Google also has a Haskell protocol buffer thing, right? You spell protocol like that? I mean, Proto lens sounds familiar. Proto lens. Okay. So I don't know if these two things are related at all, but we'll black box that and not worry about it. Okay, so We're defining a new type registered method, which takes whatever this means, empty of gRPC method type, and a request and response. And I guess the implementation is just registered method of the lower level registered method on the method type. And then service client, it will take a service as an argument and return service a function, because we're calling service client request client result. Oh, it's a type. I'm not sure exactly what this notation means. This is just three things listed. I wanted to say that this looks like a function call, and maybe it is. And then client error is just some error stuff. Client request and has stream type, gRPC method type. Did we see gRPC method type? We're exporting it. Oh, and we get it from low level. So I'm assuming that this is like streaming versus unary versus bidirectional streaming, etc. So let's have that assumption for now. So like, client request of unary, I think which they call normal. And then a request and response where, okay, so client, normal request of, okay, so now we're doing pattern matching essentially on stream type. Yeah, I guess we're doing like, do we have any pragmas? Data kinds, GATTs, kind signatures. Okay, lambda case and scope type variables. So I guess what it's saying is that client normal request is going to take a request, some timeout stuff, a metadata map, and a client request normal request response. And similarly, we're going to get one of these for each type of gRPC stuff. So this client writer request is like client streaming. Client reader request is server streaming. And then client bidirectional request is somewhere going to be some sort of bidirectional streaming. Okay. But they take different arguments, different types of arguments, right? So unary takes a request, timeout, a metadata map, and it returns this thing. And a writer request takes a timeout and a metadata map, but also a stream send request to IO. And then the reader request also takes this low-level client call, metadata map, blah, 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 stream serve response. And similarly for the bidirectional request, it takes even more stuff. The final field will be invoked once, and it should repeatedly invoke its final argument in order to obtain the streaming response incrementally. Okay. Oh, we're just defining no, wait, what? We're defining a data type, right? So this is request response where. So how does the compiler figure out which thing is which? So stream type, I feel like should be kind of this, right? And then the request is here in this case. I don't know. Is this data kinds? Let's look up data kinds. Maybe this one. Allow promotion of data types to kind level. So here's an example of the syntax. Data vec type to type, where nil is type, I guess, vec a, ze, whatever ze is, and cons is a to vec a. Yeah, I'm guessing that this syntax is data kinds. Right, standard Haskell has a rich type language. Types blah, 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 blah. The kind language, however, is relatively simple, distinguishing only regular types, kind type, and type constructors, e.g. kind type to type to type. In particular, when using advanced type system features such as type families or GADTs, this simple kind system is insufficient and fails to prevent simple errors. Consider, for example, the type level natural numbers and length index vectors. The kind of vec is type to type to type. This means that, for example, vec int car is a well-kinded type, even though this is not what we intend when defining length index vectors. Okay. With data kinds, the example above can be rewritten as data nat is equal to ze, maybe or su nat, maybe 0 or the successor of a natural number. Data vec has a type and a natural number and gives a type where nil is, I guess, vec a of 0 maybe, and cons, whatever a is, a to vec an to vec a of, I guess, the successor of a natural number. All right. So whatever is going on, this seems like data kinds. So this is like fancy Haskell. I mean, it's clear enough kind of what these things are. I was having trouble figuring out how they mapped onto this stuff. And I think to understand that, you need to read, you or I or somebody needs to read the data kind stuff. But I'm going to just assume that that's the sort of thing that's going on here. Maybe it's not exactly data kinds. Maybe it's something somewhat similar. But maybe a controversial thing to say would be that it's kind of like a workaround for the fact that Haskell doesn't have like something more like dependent types. I don't know if that's quite true, but the vector result is, I mean, the vector, a length vector is certainly a common example of it's a classic example of a dependent type that I don't think is directly expressible in Haskell, although I might be wrong. Okay, so similarly, we have client result. So this was client request, and client result is doing more or less the same thing. Client registerable is going to take a method, gRPC method type. Client register method, ll client, ll method name. Okay, so it takes a client and a method name, and it returns IO of registered method. It's doing some side effect of registering a method, I guess. Registerable normal, which I think I will just assume means unary. And these are, this is a class, and these are just instances. Okay, I guess like saying what these particular implementations of that class look like, maybe. And then we have this client request, which I think now is a honest to goodness function. And it's going to take a tuple, or no, I guess this is saying request is of type message, or like implements the message thing, and response somehow implements message. This is, I think this notation in Haskell with the equal sign, greater than sign is like a double arrow. And this means that this is like a condition of the type signature that follows. I think is how you interpret it. At any rate, so client request is going to take a lower level client, a registered method with some stream type request response stuff. And this is not the return value. This is, I guess, the third argument. It's going to take a client request parameterized by some more stuff, and it's going to do some IO, which I guess to David's question, this is where the side effect happens of a client request, client result stream type response. So I guess this means that we're going to get, this just means we're going to get a result back, presumably and hopefully with the same stream type as the method and the actual response object. And so what is it going to do? So client request with the client and the registered method and the client normal. Oh, okay. So this is, I guess, one implementation, but this is like the unary implementation. Make response, whatever this thing, this is some sort of like infix application thing, the dollar sign surrounded by angle brackets. Whatever we're going to apply somehow make response to the low level client request and give it the client and the method and the timeout. And BL is like maybe lazy byte string, some sort of optimized byte string that's faster than like the normal Haskell strings. Okay, so we're going to take the request, make it into a lazy byte string, and then I guess make it strict or something, and pass it also the metadata. And then, okay, we're going to define make response here. So make response, I guess if it's a IO error on the left, I think we had mentioned maybe in the stack video that the common error handling pattern in Haskell is to use left and right, and the error goes on the left, and then the actual response goes on the right. And I compared this to Golang, which frequently returns two return values, but the error value is on the right in the Golang case, and the error is essentially on the left in the Haskell case. But it's kind of more or less the same thing. So this is equivalent essentially to if error is non-nil, do whatever this is, or if, do whatever this is, or if error is nil, then we're in the right case and we do whatever this is. Okay, so in the case of an error, we do client error response and some IO stuff, presumably making it monadic and side effecty, printing an error, that sort of thing. If we're on the right, that is, we were not in the error case, then I guess we check whether it's a from byte string. I guess we take the response. I guess maybe we get the body and see if we can take it and convert it to a byte string. We do more error handling on the left. And on the right, we have a parsed response. And we call client normal response on the parsed response. And whatever init MD is, metadata, maybe from the response. Initial metadata, okay, trailing metadata from the response code, so like the status code, and maybe the status details. Okay. When we do the request, we get a response back. So I guess this has gone over the wire. Yeah, and then we get the response. What is sending it over the wire, though? I guess lower level client request is sending it over the wire because it's like making a call, I guess, and polling the completion queue in the C code, I guess. This is like, I think this is like send stuff down into the C code and then we get something back. And the thing we get back is, I guess, RSP. We call LL RSP body on it. Which means that before that, RSP might essentially be like a pointer to something across the foreign function interface or something along those lines. Okay. And then we do the same sort of stuff for streaming, but streaming is a little bit more complicated because we do multiple messages at once. And we're just going to black box that because that's interesting complexity, but on first pass through the code base, it's probably not so essential to understand. And we can also acquire the client, which takes an LL client config, I guess low-level client config, and I guess, I don't know if this is a tuple or if it's just parenthesizing an ordinary type, but in a client in a IO service client service. So this is the client implementation, typically generated. Okay, so this is typically generated code for the proto compiler. And it's going to return a managed service client service. And this is I guess, using whatever control monad managed is. Let's look up control monad managed. And it's going to give me some story. Manage resources that you can acquire with this. So what does it mean by managed? Does it mean like memory managed? Managed resource that you acquire with so monad managed, functor managed. Let's look at this one. Okay, I guess it wants me to read this whole, like, is there a direct description of what's going on? This library contains the managed monad, which is a small building block for wrapping resources that you require in an exception-safe way using a callback. Okay. The managed type is really simple. Managed A is managed with for all R A to IOR to IOR. And it's a special case of two other monads, codensity IOA equals for all R dot cont T R IOA. Okay, it automatically lifts the monad. It automatically lifts the monoid in num type classes. All applicatives can auto lift these two type classes by chaining applicatives. You can extend types. So assuming this is more or less the same thing, I'm not sure this is literally the same library, but the building block for wrapping resources that you acquire in an exception-safe way using a callback. All right. Managed with file, run effects. Okay. All right. Something about wrapping things safely. I guess the monad is going to manage things, maybe manage things like closing and files or like handling resources. Not sure. Okay, so back to the Haskell file. A utility. So simply simplify server streaming is a utility for simplifying server streaming gRPC client requests. You can use this to avoid client request and client result pattern matching boilerplate at call sites. Okay, so this is like a convenience utility. I guess we'll mostly ignore it. Here's a convenience utility for unary. All right, so that's client. Okay, and it's got some nice features, I guess, providing a nice interface, and then it's mostly just wrapping the lower level stuff and handing stuff off to it. And then it's got some kind of like fancy kind looking stuff, I guess, to make code cleaner and easier to read and easier to work with and that sort of thing. So here's server.hs. I'm going to guess that it looks pretty much the same as client, but let's take a look. Well, servers have handlers. Okay, so that's a good point. So server handler AB is going to be server call A, and then IO of B metadata map status code status details. So A in this case is like a request, and B is a response. So this is okay. So server handler from A to B. This makes sense as a type. What else? So we have this data server request where thing that is presumably that looks exactly like the client request with the expected things changed. We have convert generated server handler, and what is it? How's it going to convert it? I don't know. And what is it going to convert it to? So we have a server request, and it's going to so a thing that takes a server request and a server response. So that's basically a server. And it's going to return a server handler of request response. So we're converting a server request response thingy pair into this type, I guess. So it's kind of like wrapping the server into a type. So convert generated server handler call is equal to do. So call prime is going to be call with the payload equal to nothing, I guess. And it's going to call server normal response, basically unary response on the response metadata status, etc. Those are going to be those variables are going to be assigned to be the result of handler called on the request, which is, I guess, the request we just passed in, and it's going to return the stuff we the response stuff back. Right. I'm not sure really what the point of that is, but maybe just making it work better with the type system. And then convert server handler, convert generated server handler, and then convert server handler, which just takes two message A and B and has a server handler AB and a server handler low level. So given a server handler, we get a lower level server handler, I guess. All right. And then we have this type server reader handler, which is, they use reader to mean reader and writer. They have some connection to streaming and Baidu streaming. There seems to be kind of like their own language that's different from the gRPC ecosystem, but it kind of maps on in a one-to-one way, I think. And then writer handler, this is presumably all just the same stuff with various the more or less obvious changes made, and making sure that you figure out how that the types are all doing the correct thing. Convert receive message A, stream receive byte string to stream receive A. This seems to be just more conversion from one sort of type to another. I don't have a sense of why. It doesn't seem to be just conversion from lower level to higher level, although maybe that's at the root of what's going on. Conversion of, I guess, a message to a byte string. A handler type which I guess is like parameterized by a gRPC method type. And we have unary handler, client stream handler, server stream handler, and Baidu handler. And these both have messages, I guess, probably send and receive, the method name, the handler, which has the appropriate type, and the receive and response. And that's going to, I guess, return a type, handler of type normal, which means unary. All right. And then any handler is this for all A of type gRPC method type, composed, I guess, with any handler of A. So maybe this is just a way of, I don't know if you would call it promoting, but being able to use any specific type of handler and referring to it in a generic way, perhaps. Not sure. Here's handle call error. This is going to be some error handling. Handles errors that result from trying to handle a call on the server. For each error, takes a different action depending on the severity of the context of handling a server call. This also tries to give an indication of whether the error is our fault or user error. All right, so I don't know what it means by in the context. Okay. I thought at first severity meant severity in the context, but maybe it means it just depends on message severity, and the context is changing depending on the kind of call it is, perhaps. We have things like timeouts, server shutdown, benign. So we just return, I guess. gRPC IO decode error, and we're just going to log. I guess for most of these, it looks like we're going to log errors. Loop W error is going to call itself recursively. Something about mod, checking whether something has a remainder mod 100. And we're going to print, I guess, the index. No, not the index. Yeah, we have a counter. So I is a counter. I'm going to increment it. And every 100 iterations, we're going to print a line. And this is presumably maybe the monadic bind again. I'm going to handle call error, opt logger. But why? Because we're just logging. Because handle call error, I guess, is just logging. It says that it's handling the call on the server, the call error on the server. But in practice, it seems like it's either just returning in these two cases or logging a message. And so this really is a logger. It's not actually, I guess, handling the error unless I'm missing, like maybe in the log messages, is there like a side effect that handles the error? I guess this is like log error. And then maybe this is loop W error is just, it would be a normal pattern in some sort of logging system to reduce the frequency of logging by doing something like only logging every n times, and I guess here n is 100 or something along those lines. That I think that's the sort of thing that's going on. But again, I'm not a Haskell person, so I'm just trying my best to sort of figure out what's likely to be going on. All right, so here's handle loop. Maybe this is the server loop that handles requests. says to do options for setting initial and trailing metadata. Okay, so we need more options for setting the metadata that flanks each call. So handle loop. Let's take the unary case. Handle loop of SO server and options, and a unary handler parameterized by some stuff. We're going to call loop W error. So in the error loop, in whatever 0 is, and O is the options. And then we're going to call server handle normal call with S, which I think is the server. RM is some argument to unary handler, maybe something metadata. And an empty mempty, I think, is an empty mvar. We're going to apply that to convert server handler on F. Okay, so convert server handler just kind of like takes it did something like take a message, receive message type and a send message type, and like turns it into a real life server object, I guess. And so it seems like loop W. So this stuff is, I guess, calling in a loop, and the looping is done by this loop with error, I guess, is what W error is. Yeah. Handle call error. Okay. And then, but how does it actually handle the call? So int and error and server options. So int is 0. And I guess that's the starting index. And this is going to log stuff for sure. But then, okay, so the third argument is IO, either a gRPC IO error or an A. And whatever, does it do anything if it's an A? It doesn't seem to do anything if it's an A, only if it's, wait, 1, 2, 3, so 1, 2, oh, so F, I guess, is the IO thing. What does it do with F? Oh, it just calls it on itself again. So it seems to be just, F is just there so that it can be there again. And so I guess the way to think about it is that server handle normal call is going to return either a response or an error. And it's just there to kind of kick off, this is having a side effect. It's sending and receiving stuff, I suppose. And then loop error is only there to kind of wrap things I see. We get this F monadic bind that I missed. So F is not just there to keep calling it. We do, I guess, like take the output of F and handle call error on it and with opt logger. Something like that. Handle call error. What does handle call error do? Again, I guess string to IO. So I think handle call error just ignores the first parameter for the most part. So at least in these cases. 1, 2. Oh, maybe the first parameter is the log message. Is that right? I'm not sure. Handle call error, log message. Oh, no, the first was the log message. Okay, yeah, and it's just matching. Okay, yeah, all right, there we go. It's just matching on the left. So I don't know what that means on the right. The right must be this. So, okay, yeah. So if we get something that's not an error, we just return, we do nothing, essentially. This is maybe in some sense transparent. And then it's only in the error case that we kick off. Okay, so that seemed like obviously what it had to be doing from a, just reasoning like what you would expect this function to do, but it took me a moment there to figure out actually how it was doing that. And how it's doing that is it's matching on the right of the second parameter, and the second parameter is this somehow whatever the output of F is in a sense, I think. Okay, so it's handling messages and occasionally just printing errors, logging errors. All right, and then we have some server options, which is more or less just a struct, similar to the client options, and we have some default options. And then here we have a server loop. This, I don't... The server loop is going to take server options and do IO, and server loop of ops is going to be fail, registered message, method-based server loop, NYI, maybe not yet implemented. The registered method-based server loop. So I guess registration is maybe not supported. And then this might be, let's see, let's look at Haskell. This might be comments. We have the double dash is comments for sure. So what about curly brace? Multi-line comment? Yeah, okay. I think this looks like it's a multi-line comment. So this is, I guess this is telling us a registered method-based server loop. We don't have a server loop, I guess, for registered methods. And then this is maybe was an attempt or something, and it's commented out. To do, is this working? I don't know. That's what I'm going to guess. And so here's unregistered.hs. Control.arrow. I think arrow is maybe some of this left, right, error handling stuff. Control arrow, see what it is. We get this generalizing monads to arrows. If we can find it. Elsevier. I don't think Elsevier is going to let me do anything. So I'm going to bookmark this. Is this just in the is it the same one, John Hughes? Where was I? Here, John Hughes. Just curious if this paper is specifically about Haskell. Okay, well, Haskell is certainly mentioned. Okay. A new notation for arrow. Yeah, why not? I don't think I've ever read any Haskell papers, but oh, these papers and more information about arrows can be found here. All right. Let's see if we can find the papers. So we have the I guess the John Hughes one, and what's the other one? Ross Patterson, a new notation for arrows. This is arrow syntax. At 01. Do I get the PDF? All right. Cool. These are short papers. All right, so I'll read this at some point, but class category A to, I guess, a category, so arrow of A. So given an A that maybe is a category, we get an arrow of A. What is a control category? Class for categories. These look like the category theory laws, I guess. Right identity, left identity, associativity. But with like a finite condition, I guess, a finiteness condition, because we don't have infinite resources, perhaps. All right, so basic arrow class, you get first, whatever first is there a second? First, second, lift the function to an arrow, send the first component of the input through the argument arrow. We're going to throw it through the argument arrow. And copy the rest, unchange the output, the mirror image of first. Well, whatever is it? Oh, Kleisli, some sort of Kleisli category thing? Not sure. This doesn't seem to be just error handling. So whatever it is, it's some sort of fancy type stuff in the language of category theory, it looks like. Okay, so back to wherever we are, unregistered. We've got this arrow stuff. We've got some mvars, exceptions, monad, foldable, and proto3. And dispatch loop is going to take a server, some metadata, lists of handlers for each, I guess, type of thing in the API. Somewhere we get a logger, which is, I guess, the second argument. A logger is just a thing that takes strings and does I/O with them, I suppose. And forever is forever just a convention. You get one match with forever. So presumably just an infinite loop, but let's see if we can find if this comes from a library. Understanding forever in Haskell. Forever takes monadic action and repeats it indefinitely. It can be defined like this. Forever of A is equal to let loop equal A, and then I guess the non-equals bind loop in loop, which can be visualized as forever A equals A, bind A, bind A, bind A, infinitely many times. So it's like a monoid, I guess, the bind operator. If you think of this as a string, I guess, this is essentially concatenating with an operator. I'm not sure about associativity or whatever, but okay, so we're doing something forever. It's kind of like yes. Do I have yes? Yeah, yes just emits y's indefinitely. So I think that's that's the sort of thing that forever is doing. Okay, all right. And with server call async, so I guess we're doing async stuff. I don't really know how async works in Haskell now that I think about it. But we're passing in server, and we got this sc lambda. Case find handlers. So we're going to take all the handlers and whatever sc is, I guess maybe, I don't know. I don't know what the C is for, but something about servers. And we're going to find the handler and all the handlers. And if the handler is unary, then we're going to call the unary stuff. If it's client, streaming, etc., we'll call the specified handler. Mm-hmm. But how does it know which handler to call? So each message type should have exactly one handler. So I guess somehow unary handler, CS handler, SS handler, those things must all know how to handle their given message type. And all handlers is a map. Well, what is plus plus? I think plus plus is concatenation. Whoa. So maybe the way to read this is a combination of maps. Maybe it's a map from any handler to hn. Hn is, let's see, 1, 2, 3, 4. 1, 2, 3, 4. Okay. Map of any handlers to unary handlers. Map of any handlers to HC. Yeah. Okay. So I think this is like a map where the key is like this any handler type or whatever, and we're going to get back either a unary handler or client streaming or server streaming or bidirectional streaming. I don't know what plus plus is when you plus plus a map, but it seems like what it must be doing, just reasoning from what you would want in this instance, is it seems like it must be somehow concatenating, like taking the union over the maps. And I'm curious enough to actually look that up. So where does this map come from? Let's see. Data foldable, maybe? No, that you could find metadata map. Is it the metadata map? If it's in data foldable. I've seen other maps and other data things. We have fold map. Do we have just map? We have map M. We have concat map. Do we have plus plus? I don't know if I can search for plus plus. Map function. What about map concatenation? Or is it just calling, it's not fmap though, right? How can I merge two maps in Haskell? How about union with and data.map? That doesn't seem to be what they're doing, but maybe it's just calling the Haskell map function. Actually, now that I think about it, lowercase map. Yeah, I don't know. I don't know what's going on. I'm going to think of this as a union over maps. And then if anyone watching this knows what's going on with the syntax, it might be that this is just the standard map function that maps a thing over like a container of things. I think that's called map in Haskell. I'm not positive, but I don't know what the, I don't know like what this, we get many maps and they're connected by double plus signs. So I don't know how to think about that. But we have find handler, and it's going to take SC, whatever the SC is from the Lambda. And we're going to call find from, what was it, data dot foldy something, data dot foldable. And whatever this equal sign is, maybe this is like a predicate on you call method SC and any handler on method name. All right. So this is somehow going to find the handler, I guess, from all handlers. So it's going to peek inside the map and get the correct handler. And then we're going to find the types of unary handler, which I thought we had already done. But it's going to use these convert server redirect. It's these convert functions. Yep. Okay. So we're going to get the handlers somehow, put them all into a map, put them all into a bag. And when we get a request, we're going to peek inside the bag, I guess, and find the appropriate handler and handle error. Okay. What I don't know is the performance of all this. So this is being done in the dispatch loop. And it seems like I don't know if, suppose for the sake of argument that we are really unioning some maps and then peeking into them with find handler. Is this being done every time we receive a call? Because it seems like what you really want is you want to do the computation once on server start. And maybe Haskell like laziness or compiler optimization stuff somehow makes it so that once you've done this computation on the same arguments, you always like get back the same thing essentially by some sort of hash table lookup, like under the hood. I don't know. So this is just a question I have. Presumably the people the awake security people seem to know what they're doing with Haskell, right? So I assume that they've thought through the performance of this. So I'm just trying to understand as an outsider, as a newcomer, what the right way to think about this performance is. I guess let's look up Haskell lazy performance optimizations. Welcome to the Haskell Performance Resource, the collected wisdom on how to make your Haskell programs go faster. Now, this is cool. Basic techniques. Now let's look at basic techniques. The key tool in making your Haskell program run faster is profiling. Yeah, that's the key tool everywhere, I guess. General techniques: strictness, laziness, avoid space leaks. It's always a good idea. Avoiding stack overflow. I think I've seen this before, and if I recall correctly, strictness was interesting. And strictness, I think you get by like adding a bang to things, right? Or maybe not. Optimizing compilers like GHC try to reduce the cost of laziness using strictness analysis, which attempts to determine which function arguments are always evaluated by the function, and hence can be evaluated by the caller instead. Sometimes this leads to bigger gains. A strict int can be passed as an unboxed value, for example. Strictness analysis sometimes does wonderful things. For example, it is very good at optimizing FAC, maybe factorial. Okay, so if we have this recursive factorial implementation, presumably, yeah. Okay, this looks like factorial. So it somehow optimizes this. Strictness analysis can spot the fact that the argument n is strict, and it can be represented unboxed. The resulting function won't use any heap while it's running, as you'd expect. A common case of misunderstanding of the strictness is when folding. I think we are folding in here. So if you do this, without the O flag, you use a lot of heap and stack. Okay, so the thing is stored as a thunk. So I guess it's saying it's creating a func for a different thing than the programmer might typically think. And there's limitations. And then we can explicitly, I guess, create strictness maybe once we've profiled, because you should always profile. And I think that this is, oh, okay, you can use seek and then bang patterns. Okay. So I guess you have to enable bang patterns to use the bang to indicate a strict argument. Okay, so maybe strictness is the thing that's giving us performance or whatever here. I don't know. Just one question I had going down a rabbit hole. And here's so this thing that we just looked at is dispatch loop. So it's going to dispatch, I guess, the call to the correct handler. And then server loop is going to do some stuff with gRPC with server config. I guess grab the config and then given the server, do some stuff. Check whether we're done with an empty mvar. So this is like a mutable variable that we're going to store whether we're done in. We're going to call fork server on server and then run the dispatch loop, I guess, in it. And then CE finally, I don't know what CE.finally is, but we're eventually at some point going to put done. And then when launched, take mvar done. And I guess somehow if done is populated appropriately, we stop. Is that what's going on? And then we have a where clause that sets the server config. Cool. So let's take a look at these comments though. So in the gRPC library, blah, 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 doc/core/poll epoll polling engine.md seems to indicate that the thread which actually awakens from sleep on file descriptor events may differ from the one which seeks to pluck the resulting event. Okay? Thus, it seems possible that dispatch loop may be waiting on a condition variable when the server loop thread is killed. Note that pthread con timed wait never returns enter. Okay. Therefore, to awaken dispatch loop, we must initiate a gRPC shutdown. It would not suffice to kill its Haskell thread. Presumably, a gRPC shutdown broadcasts on relevant condition variables. Regardless, we do see it awaken dispatch loop. Right? I guess that's through testing or whatever. They see that it awakens as they expect. The with server cleanup code will initiate a gRPC shutdown. We arrange to trigger it by leaving the server loop thread in an interruptible sleep with take mvar while dispatch loop runs on its own thread. So dispatch loop is running on its own thread. And there's this concern about polling and waking up, which I think we're in a position now that we've kind of looked at the gRPC code and looked at this code to kind of figure out what all of that is saying. But right now I'm going to black box this and just say that there may be some concerns about threads communicating with each other properly, and specifically, I guess, polling. Presumably the polling that's done on the completion queue, which I think is where we saw pluck, and that's ultimately sending bits on the pipe between the client and the server. Then here we get a comment that says, killing the server loop thread triggers the with server cleanup code, which initiates a shutdown, which in turn kills the dispatch loop thread and any other thread we may have started with fork server. Okay, so the server loop knows to kill the dispatch thread, and anything else is started with fork server. Okay, so that's the server. All right, we can close this stuff. We're back. And that was unregistered.hs. what makes it unregistered? I guess what makes it unregistered might be the fact that it does this dispatch loop thing. Instead of using maybe maybe, I don't know if the C code typically handles dispatching to the appropriate handler, but we're definitely implementing dispatch logic here. So maybe unregistered means that the gRPC that we have our own dispatch loop essentially, and maybe the reason that I think we saw in another file that registered like services I think were not supported currently, and maybe the reason that registered services are not supported is because of this threading issue that they're maybe working around with the unregistered handler stuff by writing their own dispatch loop and having their server loop know to appropriately kill the dispatch loop. So maybe that's the sort of thing that's going on. I'm not sure. And then we have one folder left. Okay, and this is low level and unsafe and unsafe. So let's just take a look at these top level files, just out of curiosity. Okay, so we get some interesting things here in the unsafe folder, like channel args, byte buffer, constants, metadata, security, slice, and time. Let's look at a couple of these. I would expect that these are all CHS files. I would expect that they are all similar in spirit, but we'll just peek at a couple of them. gRPC unregistered.hs. I think it's a different unregistered. Not sure. Here's completion queue. Let's look at that. Was there a completion queue here? Yep. And did I open call? Not sure. Let's look at gRPC metadata map. I guess I'm not so concerned with that. Let's look, and then let's open completion queue here. So let's just see how big this is. I had kind of forgotten there was this whole folder I hadn't looked at yet of all the low level stuff. Okay, so we get this comment. Unlike most of the other internal low-level modules, we don't export everything here. There are several things in here that, if accessed, would cause race conditions. So we only expose functions that are thread safe. Cool. However, some of the functions we export here may cause memory leaks if used improperly. When definition operations which pertain to calls, this module only provides definitions for registered calls. For unregistered variants, see the unregistered file. The definitions and implementations to both are kept in completionqueue.internal. Okay, and so we get a bunch of language, I guess, prag runs or options or whatever, lambda case, multi-way if, polykines, record wildcards, or record wildcards, I guess, scoped type variables, tuple sections, rather, in view patterns. And we export a bunch of stuff, including pluck, start batch, and some other stuff like new tag. Okay, and we've got, I guess, software transaction memory, TVAR. This is like a safer version of MVAR that I think last time we, maybe in the stack repo we learned is slower than MVAR, but has better guarantees, like transactions. And then foreign pointer and foreign storable. I guess these are probably from the FFI, the foreign function interface. So we have with completion queue, whatever bracket is. So somehow it's going to bundle or like safely wrap the create completion queue gRPC and shut down completion queue. Create completion queue is, I guess, C dot is, I guess, going to call the corresponding C function. So like all of this stuff has prefix C. So this is presumably like calling across the FFI. So completion queue create for pluck is, I guess, I'm going to guess, call the corresponding C function in C.reserved. Current pluckers is going to be this transaction tvar, IO of 0, I guess, maybe initialized with 0. And similarly for current pluckers, and then shutting down is set to false. And these are like mutable variables, I guess, because we're dealing with the C world, maybe. The next tag is going to be new IORef of inbound, and we're going to return a completion queue with dot dot. I don't know what the dot dot syntax is here, but maybe that's like no like default arguments. Okay. And then start batch, a very simple wrapper around gRPC call start batch, throws a shutdown exception of some sort without calling start batch if the queue is shutting down, and then and throws call error if start batch returns a non-OK code. All right, so with permission push, not sure what with permission does. Start batch CQ call operate. Okay. At any rate, we're going to fmap throw if call error over some stuff. And that stuff is, I guess, going to like check whether we're do some debug stuff, call start batch in C and get the result, and do some more debug stuff, and then return the result. Channel create call. I guess this all seems to have the same flavor. But there is some interesting stuff like with permission. Let me see if I can find out where we're getting with permission. We'll look it up with permission. Maybe this is something. Maybe this is something custom. No. All right. So okay. So server request call. It's going to take a registered method. The C.server, I guess the lower level server, a completion queue, like a Haskell completion queue, I guess, and another Haskell completion queue, the server and the call queue, and return some stuff, either an error or a server call of the method payload. So create the call object and handle a registered call. So I think we saw request call before, but basically from the comment, it sounds like it's creating the call object and also handling the call if it's registered. We have the with permission push thing again. NB, the method type dictates whether or not a payload is present. According to the payload handling function, we do not allocate a buffer for the payload when it's not present. Okay. And with Alex, presumably like allocating some stuff. And dead call pay meta. Dead, I'm not sure. Maybe whether something is dead. So with permission pluck on the SCQ, which is the server queue, the server completion queue, we're gonna peek it. I guess peek the metadata. Create a new tag for the server queue, maybe. Debug print some debug stuff possibly. E is maybe event. And we're going to, I guess, request registered call and handle some stuff. And then check for exceptions, check whether the call is okay. And lift a server call. And that's about it. Okay. So cool. I'm curious what this with permission stuff is. Let me see if there's anything imported that looks like permission-y. So managed class accept IORef. Maybe it's part of managed. Maybe it's part of the transaction variable stuff. I don't know. Okay. All right. So here we are in unsafe.chs. So this should be a C to Haskell file. And these look like C. It says import, but I think that this is really going to like somehow turn into an include, possibly, or I don't know. No, these are Haskell. I'm not sure if these turn into C includes or if they turn into Haskell includes once they're processed. Oh, we do get C includes here. Okay. Is this like a C? Is this more of a C file or more of a Haskell file? I can't tell. We've got Haskell comments, but we've also got C style includes. So some mix, whatever the C2HS Haskell C2HS format is, I assume. And we've got these language pragma things up here. Generalized new type deriving and standalone deriving. All right. So this, I guess, since it's C2HS, we should be generating the bindings here. We have new type status details and some pointer stuff. Pointer gRPC completion queue adds completion queue, new type. So, but what does this pointer do? So it does something with the pointer. gRPC underscore completion adds completion queue. So maybe this somehow defines the Haskell type completion queue as like a C2HS pointer to with this is the underlying C thing it's pointing to. So let's assume that's the case. And then we're going to say that the completion queue, which is this thing that's, I guess, defined by C2HS, is going to derive instance show so we can print it. I don't know what happens when we print it, but we can show it. Maybe it just shows what the pointer is, or like the region of memory it's pointing to or something. And then we can have a channel, and we're going to do this. I'm assuming again that this is creating a Haskell type corresponding to the pointer to a gRPC channel, represents a connection to a server created on the client side. And then we're going to do this, I guess, a bunch of different times, like call details. All right. And then we have this function with call details, which is going to take the Haskell type call details, which is, I think, essentially like a pointer to the C type. And we've got this bracket thing, bracket create call details, destroy call details. Okay, where did bracket come from? Bracket comes from control.exception. Okay. There's some exception handling stuff. So instance def adapted from some C2HS mailing list thing. So instance storable call. I guess we can store a call. And then to know how to store the call, we need to know the size of it, the alignment, and then whatever peak is. Peak of P is going to be fmap call on peak of cast pointer P, and poke of P and call R is going to be poke of cast pointer P and R. All right, somehow translating calls, C calls into Haskell calls or vice versa. Taking the C stuff and like making it available in the Haskell world. Some more defining of types and having them, I guess, in enum. And I guess converting a C enum to a Haskell enum more or less. And maybe similar with tag. A tag is an identifier that is used with a completion queue to signal that the corresponding operation has completed. So new type tag is equal to tag of either untag, I guess a type pointer, deriving show, EQ. I guess tag is a thing that has only one function, only one operation, which is untag, maybe. Okay. And then more storable stuff, call handler. And we can uncall handler, I guess, to get the pointer. Maybe in this context means like look at the underlying pointer. In more storable implementations. Cast peak, used to unwrap structs from pointers. This is all part of a workaround because the CFFI can't return raw structs directly. So we wrap the C function mallocing a temporary pointer. This function peeks the struct within the pointer, then frees it. Because the CFFI can't return raw structs directly. Why not? I don't know. But some sort of workaround. And more C2HS stuff. Okay. Cool. This is unsafe.c2h.chs. And unsafe, I guess, mainly means completion queue stuff, right? Seems to be the bulk of what's going on. Low-level.hs. Low-level safe safe interface to gRPC. By safe, we mean all gRPC objects are guaranteed to be cleaned up correctly. Okay. All functions are thread safe. All functions leave gRPC in a consistent, safe state. And these guarantees only apply to the functions exported by this module. Okay. So this is thread safe stuff that gets cleaned up. And what is the stuff? Client call with client. Just like, I don't know if this is part of the Surface API, but we're like, I think we're above the completion queue level. And we get authorization and server call stuff. Okay. There's not much there, but defining the module. Here's slice.chs. This should be the Haskell view under the gRPC slice. In the interest of time, there's maybe not so much important here, but this is where slices would be. We do get some comments. A slice is gRPC's string type. Okay. So it's like a string. It's a string slice, I guess is the way to think of it. Or at least that's how they think of it. We can easily convert these to and from byte strings. This type is a pointer to a C type. We could also represent the type as a pointer slice. All right. So here's unsafe/op. These should be basically the same thing that we've seen in the last two files, but for the gRPC operations. We get op array represents an array of ops to be passed to gRPC call start batch. Okay. Okay, there's not a ton here. Looks more or less like there's nothing super unexpected. So just in the interest of time, we'll move along. Byte buffer should be more of the same. But let's see what the comments say. Represents a pointer to a gRPC byte buffer containing one or more slices. Must be destroyed manually with gRPC byte buffer destroy. A trivial storable instance because byte buffer type is a pointer. To do. When I switched this to a foreign pointer with a finalizer, I got errors about freeing unmalloc memory. Calling the same destroy function by hand works fine in the same code though, until I find a workaround going to free everything by hand. Okay. So it seems like, I don't know. It seems like there are some mismatch issues between what the Haskell foreign function interface kind of expects and the level of control that gRPC expects of its things that are binding to the C core. And I'm going to assume that a lot of that might be just like because Haskell makes a lot of different assumptions than C, like that it may be about the language rather than about the specific implementation of the boundary in this case. So here's client.hs, the low level. This is, okay, we've got create channel. This looks pretty straightforward. To register method is going to call C register method. We've got some stuff with like SSL certificates and stuff. With client call parent handles safe creation and cleanup of a client call with an optional parent call parameter. This allows for cancellation to cascade from the parent to server call, from the parent server call to the created client call. Obviously, this is only useful if a given gRPC client is also a server. Oh, okay. I didn't know that that's what parents were for. Or at least in this case, with client call parent. Is there also with client call parent, for servers that act as clients to other gRPC servers, this version creates a client call with an optional parent server call. This allows for cascading call cancellation from the server call to the client call. Okay. All right, cool. Is there anything interesting here? So I'm not sure where this at notation is in Haskell, CL at client. We've got this unsafe CC and run except T, run ops prime, receive initial metadata. Yeah, so I'm not understanding everything that's going on here, but I understand at least the flavor of what's going on. And I suppose if we really wanted to, we could come back at some point. So client, I saw some, what is this? This seems to be involved. MDMV is used to synchronize between callers of getMD and receive below. The behavior of these two operations is different based on their call order with respect to each other. by whether or not metadata has already been received. Regardless of call order, metadata reception is done exactly once. The result of doing so is cached for subsequent calls to getMD. So I guess MD is metadata. GetMD will always return the received metadata or an error if it occurred. All right. This is not the whole story about metadata exchange ordering, but allows us to at least have parity with the client side of the C++ API with respect to when and how metadata is exchanged. You may need to revisit this a bit as we experiment with other bindings, new gRPC releases come out, and so forth. But this gives us this gives us the basic functionality. Okay. So there's some stuff about metadata that might be hard. Okay. Client request, like client request, but allows the user to supply an optional parent call so that client cancellation can be propagated from the parent to the child. Okay, that's similar from before. All right. Yeah. So in here, I guess in the where are we? The unsafe directory, or maybe just low level. Yeah, there's some maybe you might call it some like impedance mismatch stuff between Haskell and C, and I guess there's still some working out to do about how to optimize that properly or how to think about that properly. And here's low level gRPC.hs. I think I'm going to just try to close out stuff in the interest of time. I think we've been here probably for a long time. We have gRPC call error. We can stop gRPC, shut down gRPC core given a gRPC witnessing that gRPC core has been initialized. Okay. With gRPC, functions as a proof that the gRPC core has been started. The gRPC core must be initialized to create any gRPC state. So this is a requirement for the server and client create start functions. All right. Then some IO error stuff. Row of call error, debug stuff, and thread delay seconds, which is thread delay times 10 to the 6th as an int. I guess they come in as milliseconds? No, nanoseconds? Okay. All right, so here's unregistered.hs. The with server async. So what makes it async? There must be a callback, right? Maybe this is the callback. Gets a call and then forks the given function on a new thread with the new call as input, blocks until a call is received, and then immediately handles cleaning up the call safely. Because this function doesn't wait for the handler to return, it cannot return errors. Okay, so with server call async takes an S and an F, and something about masking and unmasking. And unmask server call S, monadic bind, I think we decided, error handling, and then the success case, we're going to fork server, check whether it was a success. And if it was not a success, we're going to destroy, presumably destroy the thread we tried to fork. I don't know what else we would destroy. And where handler is unmask FC, finally destroy. I don't know what unmasking is doing, but presumably finally destroy is like a try, finally sort of like finally it's going to do cleanup. And then to do, we sometimes never finish cleanup if the server is shutting down and calls kill thread. So that maybe this is like a race condition between the cleanup code and the shutdown code. This causes gRPC core to complain about leaks. I think the cause of this is that kill thread gets called after we are already in destroy server call, and wrapping uninterruptible mask doesn't seem to help. Okay, doesn't crash, but does emit annoying log messages. So destroy is equal to, we're going to print some debug stuff before and after, and then we're going to destroy the server call. So I guess we're destroying C. We're destroying just the call object, I guess, to prevent leaking calls, maybe, presumably. Okay, so here's server handler. A handler for an unregistered server call. Byte string arguments are the request body and the response body respectively. Okay, so this is the unregistered server call. I think we are in unregistered. Is that right? Yeah. And then we have the handle normal call. We have this at notation again, whatever that is. We have unsafe, maybe unsafe server call, completion queue, initial metadata, the occasional debug stuff, run ops on called on C, CQ, and I guess a list of initial metadata, op receive message, and I guess nothing else. And then do some case analysis. And in the success case, I guess debug some stuff, call F on the SCN body and return the result. To do, we have to put op receive close on server in the response ops, or else the client times out. Given this, I have no idea how to check for cancellation on the server. Okay. Okay, so and then whatever run ops is on the call in the completion queue. Okay, I guess run ops is probably going to take the call and the completion queue and do the thing that it needs to do. And it's also somehow going to take these ops, I suppose. So on receive close on server, send message with the response, and send status from server, and then some error handling. What was I going to look up? The at notation? Lambda case record wildcards. Is it record wildcards that gives us the at notation? Maybe not. Hey. I'm just going to ignore Haskell as a search term. Oh, in Haskell, it's used for so-called as patterns. Hey, at sign really does contain Haskell. I was skeptical. The so-called as patterns. This notation can be used to give aliases to patterns, making them more readable. All right, let's try Haskell as patterns. So fib at 1:tflib as another example of the use of lazy patterns. Consider the definition of the Fibonacci given earlier. So this is some Fibonacci function. This version of fib has the small advantage of not using tail on the right-hand side, since it is available in destructured form. On the left-hand side is tfib. I guess tail is called here. And somehow... Oh, okay. So this is saying that I guess a fib is a 1 maybe followed by a tfib, like the fib tail. I'm going to guess that's what it is. Okay. There's something about patterns and making them nicer. Okay. So and then in this file, which I think was unregistered, we have more. We looked at the unary code, and then there's like streaming code and whatnot. Okay, so here's completion queue unregistered. And I guess I'm going to mostly ignore this, but what functions do we have? We have channel create call and server request call and their implementations. Okay. And then finally, we have internal completion queue / internal.hs. And how big is this? Not big, 175. We'll take a look. Note, the concurrency requirements for a completion queue are a little complicated. There are two read operations, next and pluck. We can either call next on a completion queue or call pluck up to max completion queue pluckers times concurrently. But we can't mix next and pluck calls. Fortunately, we only need to use next when we are shutting down the queue. Thus, we do two things to shut down. Set the shutting down tvar to true. When this is set, no new pluck calls will be allowed to start. And 2, wait until no threads are plucking as counted by current pluckers. Okay, this logic can be seen in pluck and shut down completion queue. There's one more possible race condition, pushing work onto the queue after we begin to shut down. Solution, another counter which must reach 0 before the shutdown can start. And to do, current pushers currently imposes an arbitrary limit on the number of current pushers to the completion queue, but I don't know what the limit should be set to. I haven't found any documentation that suggests there's an upper limit imposed by the gRPC library, but there might be. Okay. And wraps the state necessary to use a gRPC completion queue. Okay. So this is the state for the gRPC completion queue, including the tvars that includes things like current pushers and current pluckers and whether it's shutting down. And then the CQ op type is either push or pluck. And new tag takes a completion queue and returns an IO of C tag. Create a new C dot tag for identifying work items on the completion queue. So we can tag items on the completion queue, I guess, using the tags from the underlying C core code. And here's with permission. With permission safely brackets an operation that pushes work onto or plucks results from the given completion queue. Okay, so it takes a CQ op type and a completion queue, and an IO either. So whatever A is, either A or an error, and then it returns either A or an error, I guess. And so it's called with permission op CQ and act. I don't know what act is. And they're going to call, so under the hood, they're using the bracket thing from, I think, control dot exceptions or something like that. Okay, and acquire and release. Where are acquire and release given? I'm not sure. They're probably defined in a where clause. And we get a resource, got resource. And if we got resource, then act, I guess, perform some action. Else return left of gRPC-IO shutdown. Where acquire is atomically do, okay, so we're going to atomically read the tvar to check whether it's shutting down. And if it's not shutting down, I guess, do set the current count to whatever the get count is on the tvar. And if it's less than the limit, we're going to increment it essentially. Else we're going to retry. And we're going to return whether we're not shutting down. And then release of got resource is equal to when got resource, atomically modify the tvar, get the count, and subtract 1. So that's, oh, okay, so it's releasing the resource. Okay. And then we have implementations for pluck and a long comment. Waits for the given number of seconds for the given tag to appear on the completion queue. Okay, throws the shutdown error if the completion queue is shutting down and cannot handle new requests. Note that the timeout is optional. When doing client ops, provide nothing, and the pluck will automatically fail if the deadline associated with the client call expires. If plucking server request call, this will block forever unless a timeout is given. Okay, so, and then there's a variant of pluck which assumes pluck permission has been granted. Event to error translate a C event to an error. We can shut down the completion queue. All right, and that's the last file. Here's where I called yes. So that's gRPC-Haskell. There's a lot there, and we also saw that there were at least kind of 2 other attempts to implement some sort of gRPC-Haskell interface. One that looked like it was coming from Google, or at least was hosted in the Google repository. And then another that might be unrelated, which I assume is unrelated because it didn't link to the other implementation. But the other is like the direct ancestor of the gRPC-Haskell implementation we just looked at. And so it seems like there are still challenges in terms of figuring out how to implement a gRPC-Haskell kind of like in the low level stuff. But I believe if I think I looked at the README of this like a few weeks ago, or maybe their like web page or their documentation, and I believe that this is used in production. So whatever the kind of impedance mismatch issues are, they're not production blocking. I don't know if they are like it's some of those comments that there might be like race conditions. They might be very, very rare. They may not matter so much in practice, but it does seem like there's a real challenge there. So just something to keep in mind. In Python, when we looked at the implementation, it looked it looked not too bad, and that may be because Python and C kind of have a similar, like every in Python, everything's mutable, and so it doesn't necessarily have the same sort of not the same sort of gulf between at least like the mental models of the programming language and the underlying like C core that you get. So I thought that was really interesting personally, like as I was looking through that. And it definitely seems like a challenging project, but also very cool because like with that project, you can presumably build some Haskell gRPC services. And we may do that at some point just to play around with Haskell and trying to build something interesting. Okay, so that's all for me. I'll see you tomorrow. And what are we doing tomorrow? I think we might be looking at React. Is that right? But in the afternoon tomorrow, we are looking at I know that we were looking at the Twitter recommendation algorithm. Yeah. Okay. So tomorrow in the morning, we're looking at React. And in the afternoon, we're looking at the recently released open source Twitter recommendation algorithm. And that's all for me. Thanks.